Hello everyone, my name is Dr. Ambud Misra, and in this video we will be discussing about the concept of preload and afterload and some of its applications. So let's start the video. So what is preload? It actually relates to the ventricles. Okay, so by definition the preload is the wall tension that is generated when the ventricles are filled with the blood. So whenever the ventricles are fully filled, that is, we say a left ventricular end diastolic volume. So this volume is going to stretch the cardiomyocyte to its maximum length, to its maximum extent. Beyond that, the cardiomyocytes are not going to stretch further. So this left ventricular end diastolic volume is going to impose some pressure onto the walls of the ventricles. That pressure is called left ventricular end diastolic pressure. So starting with the preload, it is the wall tension experienced by left ventricle just before the onset of systole, or you can say at the end of diastole. So what must have caused this tension onto the ventricles, onto the walls of ventricles? So as we saw, like it is the blood that is inside the ventricles, that is left ventricular end diastolic volume, that is imposing a pressure, that is left ventricular end diastolic pressure. So now this pressure is going to cause the lengthening of the cardiomyocyte. So these are the factors, or you can say these are some factors which are actually interrelated to each other, and which in turn are going to contribute to the ventricular preload. So before further understanding, let's understand the interrelation of left ventricular volume and left ventricular pressure. So relation between left ventricular volume and left ventricular pressure. We will understand this using a graph. So this is your left ventricular pressure, this is your left ventricular volume. Okay, so this graph is going to look somewhat like this. So what is the significance of learning this relationship between left ventricular pressure and left ventricular volume? So you know this, at this stage, whatever blood is inside the ventricles is not going to cause any pressure onto the walls of your ventricles. But as the filling starts beyond this, you can see this relationship is linear. In earlier phase, as the left ventricular volume increases, linearly the left ventricular pressure also increases. But so here it is the linear relation of left ventricular volume with left ventricular pressure. But as you can see, this is going to follow only till certain extent. Beyond that, further by increasing the left ventricular volume, the pressure keeps on increasing. Like you can say, like beyond this stage, the myocyte length is at its maximum. Like here, you can say the ventricles has stretched to their maximum length, and beyond that they cannot elongate further. So that says even if we increase even a slight amount of volume, the pressure is going to increase much more as compared to the increase in amount of volume. So what is the limiting factor that is going to cause this kind of relation beyond certain extent? So it is a property of your ventricles that is called compliance. So after this, where this relation is not linear anymore, so the limiting factor here is your compliance of your ventricles, of primarily of your left ventricle. So what is compliance? You see, whenever you increase the volume or increase the pressure, the cardiomyocyte is going to increase in length. It is going to stretch, but is going to stretch to a certain level, not beyond that. So this ability of ventricles to stretch when there is some kind of volume or pressure that is getting imposed on it is called compliance. Compliance is basically ability to stretch. Similarly, you can see in blood vessels and in case of your lungs. So whenever the blood goes from left ventricles into the aorta and further into the arteries expand. It's their compliance that is making them to expand. So similarly, like when we breathe, our lungs expand in order to accommodate that amount of air. So that is your compliance. Compliance is ability to stretch. So here, the limiting factor that is going to play after a certain extent is your compliance of your ventricles. So here, actually compliance is it becomes a limiting factor here, and it is ability to stretch. Like in really basic terms, like you can say it is the ability of your muscle or your cardiomyocyte to stretch when getting imposed by certain pressure or certain volume that is going to cause that amount of pressure. So how can we relate this to certain pathologies? So you can see in case of heart failure, you see in heart failure the heart is not able to pump enough blood to suffice the demand of your body, to suffice the demand of the cells of your body. So to fulfill this requirement, as there is going to be decreased effective circulatory volume in case of heart failure. So what happens in heart failure? There will be the heart is unable to pump enough blood to fulfill body's requirements. That is, there is decreased effective circulatory volume. So as there is going to be decreased effective circulatory volume, so your kidneys, which are the major regulator of your body volume, like the fluid inside your body and the volume of it, so it is going to get less blood supply. It is going to get less blood as there is decreased effective circulatory volume. So whenever the kidneys sense or they get less blood, they are going to so there is decreased blood flow to kidneys. So what in turn the kidneys are going to do? The kidneys are going to conserve salt and water. And how they are going to do this? They are going to do this by activating your RAS, renin, angiotensin aldosterone system, and they also release ADH or vasopressin. They stimulate to release. So in order to conserve what salt and water, so kidneys conserve salt and water by activating RAS and ADH or vasopressin. So now the kidneys are activated because they are getting less blood supply, and they are activated, and they have now they have a goal to conserve this salt and water in order to increase the blood volume. So they are going to do this. So what they will do? They are going to increase the blood volume. So now blood volume is increased. So as the blood volume is increased, the left ventricle volume is also going to increase. So there will be increased left ventricular volume, or even say left ventricular and diastolic volume, because there is increase in left ventricle volume. So now this excess blood, uh, is going to increase the left ventricular volume, and as we saw in this relation, you know, as the blood that was earlier before the kidneys got activated, and they caused the release of RAS, they stimulate the RAS and release of ADH, which in turn causes conservation of salt and water. There was that amount of blood, that amount of end diastolic volume that was earlier, was able to stretch your ventricles to that extent. Beyond that, they are not going to be able to extend further. But as the volume has increased further due to conservation of salt and water by kidneys, now this excess volume that has come inside the left ventricle, this will going to increase the left ventricular pressure to a certain extent, that this increased pressure is going to cause congestion inside your pulmonary vasculature. So this this increased pressure inside the left ventricle is going to transmit to further to the atria, and then further into your pulmonary vasculature. So this in turn is going to, so this in turn is going to limit compliance of ventricles. Now ventricles cannot expand further, so there will be congestion of blood inside pulmonary vasculature. Now, whenever there is congestion of blood, that is increased pressure inside the pulmonary vasculature, the fluid is going to leak out of the pulmonary vasculature into the lungs, into the your air spaces, your alveoli. So there will be fluid leaks out into lungs. What does it mean? Like when the fluid from the pulmonary vasculature is going to leak out into the lungs, this will in turn is going to cause pulmonary edema. So this will cause pulmonary edema, and this pulmonary edema will result in some symptoms, that is your shortness of breath and cough. So whenever a patient of heart failure comes with symptoms like shortness of breath and cough and difficulty in breathing, so that means this indicates the sign of pulmonary edema and pulmonary congestion. Now, in second application that we are going to see, there are some kind of infiltrative diseases such as amyloidosis. So what happens in case of amyloidosis? There is, first of all, what is amyloid? Amyloid is a certain form of insoluble, and these are insoluble misfolded proteins that are going to join to each other and arrange in form of a fiber, and then in turn they are going to arrange themselves inside the cells, inside the tissues. So as they are misfolded and they cannot be they are not soluble, they are insoluble, so they cannot be degraded and cannot be cleared from from the body. So they are going to accumulate there, and they are going to hamper the normal physiology of that organ. So in case of heart, like in case of amyloidosis of heart, there is deposition of amyloid in heart wall. This in turn is going to make the walls stiff. This will limit the expansion of your left ventricle and the walls of your ventricle. So this in turn is going to affect what? Your compliance. So in case of amyloidosis, your compliance is going to decrease, like by applying certain amount of pressure, or whenever the blood is going to fill inside the ventricles are not going to expand to that extent that it used to when it was normal. So this in turn will decrease the compliance of your heart. That is, it decreases the extent of your cardiomyocyte to increase in length, to attain a certain length, so that to accommodate that amount of blood. But this is not going to happen. The compliance is decreased now. So now what happens? For whenever the compliance is decreased, so for similar left ventricular volume, the pressure is going to be more. So whenever the pressure is going to be more, the same thing is going to happen. So there is more pressure in the ventricles. This pressure is going to transmit into the atrium and further into your pulmonary vasculature, and which in turn is going to cause pulmonary congestion, and the fluid is going to leak out from the pulmonary vasculature into the lungs, which in turn is going to cause pulmonary edema, and the person will going to present with the same symptoms like shortness of breath and cough and all. So this further, whenever there is decrease in compliance of heart, there is going to be increased pressure, because that same amount of volume of blood is going to impose more pressure, because the ventricles are not going to expand. So if the let's suppose the ventricles are normal and it is going to accommodate let's just say like 120 ml of blood in left ventricle. Now the left ventricle is not able to expand that much. So even in case of like if it is not going to expand further, so even the less increase in amount of blood inside the left ventricle is going to cause more pressure. So this will in turn going to increase the pressure, which is going to cause pulmonary congestion and pulmonary edema, which in turn will cause cough, shortness of breath. So like in amyloidosis, I'm just going to tell you what are the two kinds of amyloid proteins that are going to deposit into the heart. So the first one is called AL type, that is your misfolded immunoglobulins, their light chains. Misfolded light chain immunoglobulins are going to cause AL are going to cause the deposition of AL type of amyloid protein, and another one is ATTR, that is misfolded transthyretin, which are going to deposit into the ventricles, and which in turn is going to cause the amyloidosis of heart. So now we have seen like how, uh, the left ventricular volume, the left ventricular pressure are related to each other, and how the compliance is going to play a very significant role in determining, the determining certain pathologies. And now now we will see how preload is going to get affected by heart rate, and which in turn is going to affect your stroke volume. So we are going to see the relation of heart rate, preload, and your stroke volume. We are going to see the relation. So you see, as you already know, like there are when there is the systole and the diastole are going to last for some amount of time, so whenever the heart rate is going to increase, so what is going to affect in this, like more the systole is going to get affected more, or your diastole? It is your diastole that are going to get shorter as compared to systole. So whenever the heart rate increases, whenever there is an increase in the heart rate, that means shorter diastole. It's obvious, like you cannot decrease, like how like you are going to decrease your systole, because if you will decrease the systole, there will be decreased stroke volume, like there will be decreased amount of blood that is going to eject, that will be going to be ejected from the left ventricle. So like in any condition, the heart will want to preserve the stroke volume, so it is going to sort of the diastole. It is not going to, like it's not actually possible to sort in the systole. So whenever there is shortening of diastole, means there is less time spent in diastole. That means there is going to be less filling. So this less filling means there will be decreased left ventricular in the diastolic volume, which in turn is going to decrease the left ventricular and diastolic pressure. It's obvious. So as we saw, like the left ventricular and diastolic volume and the left ventricular and diastolic pressure is the representation of your preload. So now they are decreased, so your preload is also going to decrease. See, the left ventricular and diastolic volume will decrease. This will decrease the preload. So this will in turn is going to decrease the stroke volume. Why? Because earlier there was more blood inside the heart to pump, but now, as you know, diastole has got shortened, and the filling is now less. So less blood is so there is less blood inside the ventricles now. So if there is less blood, the heart is going to pump less blood. So in turn, the stroke volume is going to get decreased. So can we say, like whenever the preload is going to, the preload is going to decrease, the stroke volume is also going to decrease, keeping all the variables unchanged, like all the other pressure and all the walls are functioning normal, your aortic pressure is normal, and your conducting capacity of the heart is normal. So keeping all those variables unchanged, whenever there is decrease in preload, stroke volume is going to get decreased. So can we say, like, preload is inversely proportional to HR, your heart rate, and your preload is directly proportional to your stroke volume. but keeping other variables unchanged. For example, your aortic pressure. Okay. Now we have seen everything about preload and some of its basic applications. Now let's dive into the concept of afterload. Afterload. So, in basic terms, what is afterload? Afterload is the force, that is going to oppose the contraction of your ventricles during the systole. So, in the basic definition of your afterload is it is the force opposing the ventricular contraction during systole. So this is the force opposing the ventricular contraction during the systole. Can we also say that this is the force, against which the left ventricle, that the left ventricle, need this force that left ventricle needs to overcome, in order to, pump the blood from from the left ventricle into the aorta. So there is this capacity of left ventricle to pump the blood, but there is some opposing forces that are going to oppose that contraction, or you can say those that force against which the left ventricle needs to work in order to overcome that force and pump blood from left ventricle into the aorta. So in basic terms, this is what you can say is afterload. Or can you say that the extent and the velocity with which the left ventricle is going to contract whenever it is going to push the blood that is present inside the left ventricle into the aorta? So all these things are really interrelated to each other, and one thing going to give rise to the other thing, like the opposing force. What is the opposing force? So in order to overcome this opposing force, the left ventricle needs to contract in certain way, with certain velocity, to the certain extent. So these all are are going to generate other variables. So if so, like we are saying again and again, the forces that are going to oppose. So let's see what are all those forces that are going to oppose the contraction of your ventricles. So first, you must have heard of these basic terms like blood pressure, the systemic vascular resistance. So first we will see what is the relation of systemic vascular resistance and your blood pressure. So if we see, like systemic vascular resistance is one of the contributing factor that are going to give rise to your afterload. So what is systemic vascular resistance? This is result of certain properties, or you can say certain factors. First one, it is your vessel diameter. Your vessel diameter, the first factor. How the vessel diameter is going to contribute to your afterload? See, vessels have a diameter, and whenever these vessels are going to constrict, there will be increased systemic vascular resistance. But why? You must have heard, like in the physics, like when there is a there is a column of blood, or like a column of blood is flowing into a pipe, like you can say, this flow of that fluid is going to impose some pressure onto the walls of that carrier which is carrying that fluid. So in this case, the blood that is flowing inside the walls of your vessels, this column of blood is going to impose some pressure onto the walls of your vessel. That is your blood vessel. So whenever we are going to constrict, the vessels are going to get constricted, the diameter is going to get decreased, the blood pressure is going to get increased. So how intense it is going to affect the blood pressure. So whenever the vessel diameter is going to decrease, your BP is going to increase, and vice versa. Like when it is going to increase, your BP is going to get decreased. So now you can see like how your systemic vascular resistance is your blood pressure is a contributing factor to your systemic vascular resistance, and that is because of your vessel diameter. So blood pressure is one of the factor that is going to contribute to your systemic vascular resistance. Second, can we say it is your blood viscosity? It is your blood viscosity. So whenever the blood is going to be more viscous, the viscosity of blood is going to increase. There will be increased systemic vascular resistance, because the left ventricle will be needing more force to push the viscous blood, into to further onto the in the column of your inside the blood vessels. So there is direct relation of your viscosity of your blood to your systemic vascular resistance. And the third one is your blood vessel length. So these three factors, your vessel diameter, the viscosity of blood, and your blood vessel length, is going to contribute to your systemic vascular resistance. And the blood pressure is one of the factor that is going to contribute to your systemic vascular resistance, and that is affected by the diameter of your vessel. So whenever the vessel is going to get constricted, the BP is going to get increased, and vice versa. So how, like, if we say in other terms, if we see like how the blood pressure and systemic vascular resistance is related. So there is this formula: the mean arterial pressure, or we can say in other terms, your blood pressure is equal to your cardiac output multiplied by your systemic vascular resistance. So this is your blood pressure and this is your systemic vascular resistance. So let's just say you had vasodilation. So whenever there is vasodilation, there is going to the blood pressure, the BP, is going to get decreased, and when the BP is going to get decreased, your systemic vascular resistance is also going to get decreased. Now, so can we say, like, in case of vasoconstriction, there is increased resistance, increased blood pressure. So the blood pressure and systemic vascular resistance are interrelated to each other, because the major contributing factor to the SVR, the systemic vascular resistance, is your blood pressure. What is the second factor? The second factor is your vascular compliance. It is your vascular compliance. See, whenever the left ventricle is going to go eject the blood from the cavity into the aorta. So in order to accommodate that excess blood, that amount of blood, into the aorta, the walls of aorta needs to, get stretched in order to accommodate that extra amount of blood in very less time. So the blood vessels have this capacity, to expand whenever the ventricles are going to eject the blood into the aorta. So this this compliance is similar to your ventricular compliance, but let's apply this in the context of your blood vessels, mainly your aorta. So whenever the ventricles are going to contract, it is going to eject large amount of blood that aorta needs to accommodate. So it is going to stretch. So this is called compliance. So if your vessels, the blood vessels, your aorta is stiff, it is not expanding to that extent that it should in order to accommodate that much amount of blood. So the workload by the left ventricle is going to get increased, because in order to pump that much amount of blood into stiff arteries, such as in case of your atherosclerosis, or in case of other calcification of blood vessels, the blood vessels gets more stiff. Their compliance are going to get decreased. They are not going to stretch to that extent that they used to when they were healthy. So in order to accommodate that much amount of blood, the left ventricle needs to work more, in order to stretch the arteries, the aorta, to that extent to accommodate this amount of blood. So whenever the vascular compliance is going to get decreased, your afterload is going to get increased, because now the ventricles are bound to work more in order to push that extra amount of blood into the aorta. So now you see this distension of your blood vessel. So how that much amount of blood moves further into the your blood column, further into your your arteries. So the moment left ventricle is going to get contract or compress, the blood is going to get ejected from your left ventricle into the aorta. Aorta is going to get stretched in order to accommodate that extra amount of blood. But the blood vessels, the aorta is elastic. It is going to compress further again. Whenever it is going to stretch, it is going to come back to its original position. So the moment blood is in aorta, it is going to stretch and it is going to compress further. So whenever it compresses, the blood that was present in that column is going to get pushed forward. So when this blood goes forward to the next column of your blood vessel, so from here it goes to here. So now the blood vessel that is the length of blood vessel that is ahead of that column is going to perform the same thing. That has to accommodate that blood that was pumped by that portion of aorta. So that is going to again stretch, and that is going to again compress. So this compression, this stretching and compression, this thing moves like moves forward in a orderly fashion. So this compression of your blood, this stretching or dilation of your blood vessel is what is felt as your pulse. So whenever you check for a pulse, your cardiac pulse or brachial pulse or any pulse or anywhere on your body, so this dilation, this stretching of your blood vessel is felt as pulse. So this is the concept of pulse, like I just told you. So if the arteries are stiff, like in case of atherosclerosis, or in case of calcification, this in turn going to decrease the compliance of your blood vessel, decrease the vascular compliance, which in turn is going to increase your afterload. What is the next contributor of your afterload? So in order to understand this, first we need to understand, Laplace law. Laplace law. So what is Laplace law? Laplace law in physics, it is for uh, a sphere, like a spherical body that has some amount of thickness and has a cavity inside it, and that is containing a fluid. So can you see the similarity of this to your ventricles? Like ventricles, like they are not, spherical in shape, but they has this shape, they have some thickness, and they has a cavity that is filled by some fluid, that is your blood. So this Laplace law, this says that the tension in left ventricle myocardial fiber, which is equal to transmural or intracavitary pressure in left ventricle multiplied by radius of ventricular cavity, and the whole is divided by 2 times the wall thickness of your left ventricle. See, if we see this by a diagram, so this is your tension, the tension that is inside the walls of your left ventricle. This, this is the radius of your ventricular cavity. This is your wall thickness, or you can say small t. This is your wall thickness. And what is transmural pressure? What is transmural pressure? Heart is situated inside your thoracic cavity. So there is some pressure inside your ventricles, that is your intracavitary pressure, and there is some pressure that is outside your heart, that is the the pressure that is present inside your thoracic cavity. So transmural pressure means the pressure that is inside the ventricles minus the pressure outside the ventricles. So that is your transmural pressure, the difference of pressure in between the wall, like around the walls. So like inside it is your ventricular pressure, outside it is your intrathoracic pressure. So transmural pressure is intracavitary pressure minus your intrathoracic pressure. But as you know, the intracavitary pressure is much more in comparison to your intrathoracic pressure. So we can, to some extent we can neglect the intrathoracic pressure. So we will only consider your intracavitary pressure. But in some cases, such as when the patient is on positive pressure ventilation, so in that case the intracavitary pressure, intrapulmonary pressure is much more, like the pressure, intrathoracic pressure, sorry, not pulmonary, intrathoracic pressure is much more. So we cannot neglect in case of like positive pressure ventilation. But here, like for now, like we can neglect in like normal physiological conditions, we can neglect this intrathoracic pressure. So like if we see some cases, like in case of, like we will understand this by one case, like in case of your dilated cardiomyopathy. So what happens in dilated cardiomyopathy? Your walls of your ventricles has got weakened, and the chamber size, the ventricular chamber size has increased. So you know, uh, because the muscles are weakened and there is increased cavity size of your left ventricle. So increased cavity size means, can you say there is increased radius of your ventricular cavity? Yes, you can say that. And now, if the cavity size is increased, the left ventricle is now able to accommodate more blood, comparatively, because the cavity size is more. So, can we say like intracavitary pressure in left ventricle is increased in case of dilated cardiomyopathy? Yes, because the blood is the left ventricle, the dilated left ventricle is going to accommodate more blood as compared to before when it was normal, and the radius is also increased because the cavity size has been increased now. So both these factors are now increased. So can you say the tension in the myocardial fiber is increased, right? So this increased cavity size, increased radius of ventricular cavity, increased intracavitary pressure due to increased blood volume, or you can say increased filling, which is in turn is going to get transferred as your increased in wall tension, increased in wall tension. So like wall tension is your afterload, right? So whenever the tension is wall is more, like whenever the left ventricle has to work more, or like work more to the force that is opposing it, the tension is going to more, because ultimately the afterload is your tension that is going to be in your left ventricle when it is going to contract against that pressure which is going to oppose it. So increased wall tension means increased afterload. So if your afterload is more, can you say your stroke volume is going to get decreased, right? So like in case of dilated cardiomyopathy, your stroke volume is going to get decreased. So we have seen the factors that are going to contribute to afterload, that is your systemic vascular resistance, how blood pressure is going to play a role in determining the afterload, the vascular compliance, how in case of calcification and atherosclerosis there is increased afterload, and which in turn causes decrease in your stroke volume. And in Laplace law we saw in case of dilated cardiomyopathy, whenever the cavity size increased, so there is big increase in afterload, and further there is decrease in stroke volume. If we consider hypertrophic cardiomyopathy, in case of hypertrophic cardiomyopathy, what happens? The chamber size could be normal or could be decreased, but the ventricular walls are now hypertrophic. The thickness of your ventricular wall is more now, and the cavity size is reduced. But if you put that in this formula, you will see increased wall thickness and decreased cavity size. This will in turn decrease the tension. But still, in case of hypertrophic cardiomyopathy, there is decreased stroke volume. Why? Because in case of hypertrophic cardiomyopathy, the intracavitary volume is going to get decreased, and the decreased wall tension is not sufficient enough to eject whatever amount of blood is there in the left ventricle. So ultimately the stroke volume is going to get decreased because there is not sufficient blood to eject from left ventricle. So in that sense, the stroke volume is going to get decreased in case of hypertrophic cardiomyopathy. So the last thing that we are going to discuss now is your Frank Starling mechanism. What is Frank Starling mechanism? Frank Starling mechanism is the relationship between stroke volume and your left ventricular and diastolic volume. It is relation between your stroke volume and left ventricular and diastolic volume. You will understand this by a graph. This is your stroke volume and this is your left ventricular and diastolic volume. The graph, the plot is somewhat like this. Okay, how? You see, stroke volume increases with increase in left ventricular and diastolic volume, but only till certain extent. See, this is linear, but until certain extent. Beyond that, by increasing the left ventricular and diastolic volume, the stroke volume is not going to get increased. So as we saw when we were seeing the relationship between the pressure and the volume of your left ventricular, the left ventricles, the limiting factor there was your compliance, the compliance of your ventricles. So what is going to be the limiting factor in this case? So in this case, the limiting factor is going to be your contractility. The contractility of your left ventricle is going to play as a limiting factor in case when we see a relation between stroke volume and left ventricular and diastolic volume. How? See, at physiological level, the ventricles has a limit. They can contract to a certain limit. Like they cannot contract beyond their capacity. So the contractility is such a factor which is going to limit the stroke volume, which will be independent of increase in left ventricular and diastolic volume after certain extent. That is because of your contractility. So whenever we are going to increase the left ventricular and diastolic volume, the stroke volume is going to get increased, but beyond certain extent the relation is not linear anymore. So what is the application of this? In case of administration of positive inotrope that we see in the last video. So the positive inotrope, these causes sympathetic activation. So the means the adrenaline and noradrenaline is going to activate your beta receptors, which further in going to increase the contractility. So in physiological limits you will going to see this kind of graph, but in case of positive and when we administer positive inotropes, now they are going to increase the intracytoplasmic calcium, which in turn is going to increase the contractility and the heart rate. So whenever the contractility is going to get increased, don't you think at certain increase in your left ventricle and diastolic volume, there will be more increased in your stroke volume. So your graph is going to shift upwards. That is your case of positive inotropes, right? In what cases the graph is going to shift downwards? In all those cases where your contractility is going to get decreased. So what all cases can you think of where your contractility is going to get decreased? One is your ischemia. Like in case of ischemia, the heart is not able to, contract sufficiently, like that it was doing normally. And also in case of heart failure, in these two cases, your contractility is going to get decreased and your graph is going to shift downwards. That is in case of ischemia and heart failure. And this is your in the normal condition. So you see how when we establish a relation between stroke volume and left ventricular and diastolic volume, the contractility of heart is going to play a role of a limiting factor. And when we see a relation between left ventricular pressure and left ventricular volume, your compliance is going to be a limiting factor. So this is all for today's video. I hope you enjoyed this, and please do let me know if you want any specific topic that you want me to discuss here. Please let me know in the comments, and we will discuss about it in the next video. So thank you all for watching the video. Have a good day.